In the first part of this unit on compression, we'll try to exploit character frequencies. And before we get there, let's talk about encoding characters in binary from first principles. It's the simplest form of encoding, and we need it anyways. Whatever kind of string we want to store in a computer, we have to somehow encode it as bits. And a character encoding just means that we have a certain code for each source character, for each character in the source text. So you can represent it as a function e that maps from the source alphabet to potentially several characters in the coded alphabet. Right? It can be a code word. That's what we call these. The representation for a single character is the code word for that character. In this case, we'll usually assume the source alphabet is fairly big, whereas the coded alphabet might be just binary. In principle, that's all of these things are called character encodings. There's two types that we distinguish. One where all the code words have the same length, and these are just simple to work with because you can compute where exactly the ith character in the coded text starts. But there's also variable length codes that have better compression properties. So we'll look at both briefly. The most widely known example of a fixed length code probably is this ASCII character encoding. Stands for American Standard Code for Information Exchange and is a little dated. As I alluded to earlier, it just has the Latin alphabet plus a few extra characters, and that is it. It has a lot of these weird control characters. That's from the time of needle printers, where you had to tell the printer to go to the next line and all that. So a third or so of the encoding that we use is completely useless because it uses movement commands that our devices don't use anymore. But that's how standards are. They tend to stick around. ASCII uses 7 bits for each character. In files, it's often added. There's an 8th bit added that is, in the strict sense, for ASCII is always 0. Well, just as an aside, this extra bit is then used for extended ASCII. So there were extensions of this for various European languages where you had a few extra characters, but it would still be 256, so not enough for many scripts. Anyways, standard ASCII is just these 128 characters. It's very limited, but it's very simple. That's the good thing about it. So both encoding and decoding are as fast as you can possibly get. You can do it by table lookup, and it's very regular. It will probably use more space than necessary unless all the characters are equally likely to occur. And of course, it's super inflexible. What if you invent your new favorite emoji, then you can't represent it. Let's have a brief look at variable length code and also start with a historic example, namely Morse codes. So it might look like variable length code is a new invention, but that's not the case. And it also here, for Morse code, I think people usually list things like this. That's a translation from standard characters. Oh, by the way, there's more than one Morse code. This must be super confusing if you're like you're lost on some remote island. Which Morse code should I use? This is the international Morse code allegedly used with ships at sea, but don't quote me on this. But this list tells you what character maps to what sequence of short and long tones, right? So you know this boop, 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 for SOS and so on. Right. What you often don't see is this is convenient for sending code, but for decoding back from the patterns to the letters is actually not very convenient, because you would have to find, what does ... long mean again? Short, long? Ah, it's a U, because it's just enough for me to walk around. There's another representation of the same information that's much more convenient for decoding. And that's this kind of tree where, yeah, there we go. Good. Fire alarm still works. So relieved. So we can represent the decoding as this tree where at each point you have to decide, is the next thing you hear a dot or a dash or a long? And then you just follow along. So if I have dot, dot, long, I end up at U without having to search in this table. So one piece of information, encoding and decoding sometimes can use different representations to be more efficient. Right. Well, what to take away from this slide is just, oh, these representations have different lengths. So it's a variable length code. Quick fun question. How many characters are in the coded text, in the coded alphabet? So remember, source text is the thing you start with. Coded text is what you end up when you encode it. And I'll go back to that slide. Okay, I haven't listed anything here. So source text is usually the thing that is useful for humans, right? And then the coded text is something for computers to deal with. Okay, we have lots of votes in. Let me show the distribution. Quite a spread. Not so many picked the right answer. I know it's a tricky question. So first of all, the source alphabet isn't even specified explicitly, but it's kind of listed here. So the source alphabet would be just the capital letters and the digits. And that, I guess, adds up to 36. But that's the source alphabet, because that's the part that's useful for humans. The coded alphabet, well, it has to be the short and the long. But there's actually a third character that's hidden. It's not represented here, which is a pause. You can't actually use Morse code if you just use shorts and longs. And if you try decoding here, you see why. If I send you dot, 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 I could mean 3 E's, or I could mean 1 S, or 1 E and 1 I, or vice versa. So it's totally ambiguous. I have to leave a pause between each letter. That's not represented in the table, but it actually is needed here. Otherwise, the code wouldn't make sense, or it's not ambiguous at least. It's not unambiguous. That's why 3 is the right answer for this one. Okay, you're probably not going to be in the Navy, so I'm not sure if you need to know Morse code. This slide is more important for us. Now, interestingly, UTF-8 still is a variable length code, despite this 8 looking like it should be 8-bit each time. It's a little bit misleading. UTF-8, we covered this yesterday or when it was. It is an encoding from the Unicode standard that is able to represent pretty much any kind of symbol humanity has invented, 150,000 different ones. UTF-8 is a specific way to encode those that's used for text files all across the web. Okay, that's out of date. I have to update the slide. Keeps changing. So it's more like 150,000. Well, and counting is the important bit. Now, it's a variable length code because it needs between 1 and 4 bytes for one character. It reserves the short code word of 1 byte for the ASCII characters because still, by and large, a lot of text is using those characters. And the non-ASCII characters are encoded using that kind of scheme. So they're classified into different categories, and some of them are encoded with 2 bytes, where you specify how long the sequence will be in the first byte by having 2, 3, or 4 ones at the beginning, followed by a 0. And then each subsequent byte has another code that wouldn't be strictly necessary, but this is for making it so that you can, for an individual byte, recognize whether it's part of a larger symbol or is an individual character. So again, the details of this encoding are not so important. I just want to point out that it is a variable length code. The benefit of leaving ASCII as part of this is whenever you use just the ASCII characters, you don't actually waste any space. You would have rounded up to 8 bits for alignment anyways. But you can include arbitrary Unicode characters in the middle, and those need a bit more space. But if that's English text with a few emojis sprinkled in, it's a very efficient encoding. Now this has, the fact that this is a variable length code has some consequences that most programmers tend to ignore most of the time and get away with most of the time, but not always. If you have a text that's encoded in UTF-8 and you want to know how many characters there are, you can't just take the length of the file or the number of bytes. You would actually have to read through all the bytes, all the text, and check which of the bytes are part of actually the same character. Likewise, if you want to jump to character 1527 in the text, you don't know exactly where to jump to. So the variable length code nature of this makes algorithms much more complicated, which is one reason why Java tries to avoid this a bit by using UTF-16 instead. So you have only very rare exceptions, but even there, it's a variable length code if you're strict. All right. So much for the real-world examples for now. From a more theoretical perspective, there's one thing in variable length codes that you can trip over, and that's worth discussing a bit in detail because the various examples we've seen have different solutions for this. Say we have this kind of code. It's a small alphabet, and there's one code word for each letter. So we can take a word like banana over this alphabet and code it like this. Okay. And you see how this matches the letters. But the same coded text can also be decoded to another word, a different source text. And that's equally valid in a sense under this code. And in a sense, this is indicating that the code is broken. It's fundamentally broken because it's not ambiguously decodable. It's not it's ambiguous. It's not unambiguously decodable. So we don't like that kind of code. One indication that there might be a problem in your code is if one code word, like 10, is a prefix of another code word. Because then when you decode, you don't know whether you should stop and report the letter you currently have or keep reading. Now, this is not always a problem if you have this prefix property. Maybe there is a way to disambiguate it later, but a sane choice is to pick a prefix-free code that forbids that situation. No code word is ever a prefix of another one. That in particular, this class of codes is also called instantaneously decodable, because if you scan through the coded text, you can immediately report a character as soon as you've seen a code word. You don't have to think ahead of time, oh, maybe I'll have to backtrack or anything like this, as you would like in this situation. As soon as you've seen a code word, you can spit out the source character. So often, for variable length character encodings, we restrict our attention to prefix-free codes because they're fast to decode and they avoid ambiguity by definition. Now, it sounds like this is maybe an inconvenient thing to check, whether a code has this property of being prefix-free. But there's a nice way to do it by representing the code words in a trie. Now, a trie is a data structure for storing strings that we'll come back to in much more detail in Unit 8. This was the only place where reordering the units caused something to be a forward reference that would have been a normal recall this from the last unit otherwise. But I think it's fine. For this unit, just think of a trie like in this example. You have internal nodes, and then you have different letters on the child edges. And such a tree is representing a set of strings by reading the path down from the root to the leaf representing the string. So for example, 0, 0, 0 gives you the space character, or 1, 0, 1 gives you E, and that matches these code words. Now here's the trick. If you ever had, like in the previous example, like here, this ambiguity where, what was it, E, N was 1, 0, and S was 1, 1, 1. 1, 0, 0. If you had a situation like this, and you were to insert those into a trie, you would start by going to the right with a 1, then you would go left with a 0, and then here you would want to say, this is character N, but then I also want to go right with another 0 and go to S. So you can recognize this situation that one code word is a prefix of another one by running into the trouble in the tree that there's a letter associated with an internal node. Vice versa, if we say all the code words, all the letters are only allowed in the leaves of this tree, we definitely have a prefix-free code. Okay? That's why we often represent these codes as a code trie, because then it's obvious that they're prefix-free. It's also convenient for encoding and decoding. So if you want to encode something, you want to use a table like this. So if I want to encode an AND, right, I just look up A is 0, 1, N is 0, 0, 1, space is 000, then another A, 0, 1, another N, 0, 0, 1, and a T for 1, 1. But if I want to decode, I don't want to search that table. That's inconvenient. Instead, I use the trie. So we start at the root at the beginning, and then we read following the steps. So we read the first 1, then we're here. We read another 1, brings us from here down there, and we have a T. So the first letter stops at this point. Then we start at the root again. We read a 1, that brings us down here. We read a 0, brings us down here. Read another 0, brings us down here. An O. And so on and so forth. Okay? So for the next one, you read 0, 0, 0. So you have the space. Then you read 1, 0, 1. Then 0, 1, A. And 1, 1, a T. Okay, so again, two different representations of the code. One is more convenient for encoding, one more for decoding. Last part of this, just a general point again. If you pick your favorite encoding for your characters, you have to somehow tell the decoder, the person who decodes, what that code was. Otherwise, they cannot decode. So the question is kind of who watches the watchman, who decodes the decoder, and there can be different choices. It can either be a fixed coding that all people in the world know. For example, Morse and UTF-8 are of that type. You may have to tell your program that you're using that encoding, but then it knows what it is because it's a public standard. Or you can use a way to store the character encoding as part of your coded text. That's called static coding, where We'll see an example next time. You basically first send the encoding and then the coded text using that encoding. And the last option is don't even have a fixed code. That doesn't work with our character encoding so well, but you can do it with adaptive Huffman encoding as an aside. Here the idea is that you build up the code along the way, and you don't actually have to tell it up front. The decoder just retraces your steps and will always arrive at the same point in between.